Okay, hello everyone, and welcome back. I would like to talk today a little bit about isothermal coordinates on minimal surface. Okay, so let's talk first about, so again, what's our setting? We have an immersion of a planar domain. Into R3, and let's give the planar domain coordinates U1 and U2. And we're going to we're supposing that that the image of the immersion is a minimal surface in R3. Okay, but for right now, I want to talk a little bit about about what information we have. The immersion this induces a metric and the coefficients of the metric tensor are given by taking the coordinate derivatives of the immersion and then taking Euclidean inner product. So here, this is the Euclidean inner product. And this gives a 2x2 symmetric and positive definite matrix at each point. So we already know that since this is the spectral theorem, by the spectral theorem tells us that since this is a 2x2 symmetric positive definite matrix, you can locally choose a basis to make this matrix diagonal. But there is another case in which all of our formulae for the surface end up being very nice. So when this metric has the form that is lambda squared times the identity, we call this choice of coordinates and the immersion isothermal. Some people would also call these conformal coordinates. Some people would call these conformally flat coordinates. It's all the same notion. So what does this condition say? This says that G11 equals lambda squared equals G22, and that the off-diagonal elements G12 are 0. Okay, so a lot of things end up being very nice in this situation. If so it's fairly straightforward to verify from formula we showed before. So if U1 and U2 are isothermal coordinates, then the determinant of the metric is, of course, lambda to the fourth. Also, the mean curvature has a very nice form. So you can see this because so this one comes, so this formula for the determinant metric comes immediately from this guy here. If I take the determinant of this guy, I see that I have a lambda to the fourth here because I have a lambda squared here and a lambda squared here. This comes from the fact that I have the trace of Hij, which is going to be the trace of of lambda to the -4 times the identity matrix times Hij. And then if you go through and carry out that computation, you see that you get exactly, I have a factor of 1/2 here. The mean curvature is 1/2 the trace. I'm going to get lambda to the -2 H11 plus H22. Okay, so from these formulae, we see that we're going to see also later on in a minute that the existence of these isothermal coordinates give you other very nice properties. So let's see the first one. So the first lemma says that what? So again, just take our usual setting. We have an immersion. And let U1, U2 be isothermal. Then the Laplacian of the position vector is 2 lambda squared times the mean curvature. Times the normal vector, right? Okay, so let's go ahead and let's prove this. And the place to start is the defining equation for isothermal parameters, namely, so the first defining equation of isothermal parameters is this one, which says that the Euclidean inner product of d1 psi with itself is equal to lambda squared is equal to the Euclidean inner product of d2 psi with itself. And the second defining equation is this one, which says that the Euclidean inner product of d1 psi with d2 psi is equal to 0. Okay, so now I differentiate this first equation with respect to U1. Write this down. So if I differentiate with respect to psi1 in the first equation, I see that d1 squared psi twice d1 psi is equal to twice d1 d2 psi with d2 psi. The second one, so this equation comes from differentiating this guy with respect to U1, the U1 variable. If I differentiate this one with respect to the U2 variable, I see that d2 d1 psi d2 psi plus d1 psi d2 squared psi equals 0. Okay, so from this, so if I combine these two, I'll see that d1 squared psi d1 psi minus d1 d2 psi d2 psi is equal to d1 squared psi d1 psi, but I can replace this term here with minus that, and I get plus d2 squared psi d1 psi right, so I should have 0 is equal to that. And now I can write this as d1 squared psi plus d2 squared psi with d1 psi. And all of this is equal to the Laplacian of psi d1 psi. Okay, so I've just shown that the Laplacian of psi as a vector is orthogonal to this tangent vector. So if I do derivatives the other way around, I see that d1 d2 psi with d1 psi is equal to d2 squared psi d2 psi, and I differentiate the second equation with respect to the U1 variable, I'll find D1 squared psi D2 psi plus D1 psi D1 D2 psi equals 0. I combine these two equations as I did with the previous one, and I find that the Laplacian of psi as a vector is orthogonal to the second tangent vector. This guy. So what do I conclude here? I conclude that the Laplacian of psi is normal to the surface. In other words, it must point in, it must be parallel to n. So I must have the Laplacian of psi is something times the normal vector. And now we have to find out what that multiple is. Okay, and how do I find out what that multiple is? Well, I just take a dot product. So the Laplacian of psi dotted with n, this is by definition d1 squared psi with n plus d2 squared psi with n, which is now h11 plus h22 by definition of the second fundamental form. But now from the formula we had above, this is 2 lambda squared times h. And that completes the proof. So we see then that the Laplacian of the position vector, Laplacian of the position vector gives you the mean curvature in the case that you have isothermal coordinates. So right now, the following lemma. Actually, this isn't really a lemma, I should state this as a corollary. Then we see this immediately from what we have just shown, that that if I have an immersion in isothermal coordinates, then this surface is minimal if and only if the immersion is harmonic. And we can say this another way by saying that the coordinates, a surface is minimal if and only if the coordinate functions restrict to harmonic functions. And this gives an entry point for complex analysis into the theory of minimal surfaces. It says that locally, your minimal surface is really determined by 3, or in the case where you have higher codimension, n for n greater than or equal to 3 harmonic functions on the surface. Okay, so we're going to introduce some notation. This is following the book by Osserman, which again, we highly recommend. What do we have? We have as above, U1 and U2 are our local coordinates in the domain, my domain omega. And then I'm going to define my functions phi k. Let's write it this way. Let's write my function z is u1 plus I. u2 is our local complex variable. And let's define the function phi of the complex variable z as d psi du1 minus I d psi du2. And one can, of course, write this in components. Okay, so what do we see from this? The first thing we see is the Kosher-Riemann equations. So what do the Kosher-Riemann equations say? If I take d phi du1, I'm going to get d squared psi du1 squared. Let me write it this way. And if I take d psi du2, I see, or let's write it this way. So d phi du1 minus I d phi du2 is equal to exactly d1 squared psi plus d2 squared psi, which is Laplacian psi. And we see that this is equal to 0 exactly when the surface is minimal. And what we conclude from the Kosher-Riemann equations is that these three parameters, phi 1, phi 2, phi 3, are holomorphic functions. If and only if psi is, if the surface is minimal. Okay, what's the next thing we conclude? The next thing we conclude is, well, we have to compute what is the length of phi. So this is the length of the vector d1 psi minus I d2 psi. And this is exactly, let's write this way, squared, squared. It's always easier to compute length squared, d1 psi squared plus d2 psi squared. So phi squared is not equal to 0 precisely when the immersion, this mapping is regular / n immersion. And the last thing we can compute is the square. So that's the first thing we see. Finally, we see that what is phi k squared? So this is going to be d1 psi k minus I d2 psi k squared. And this is the length of d1 psi k psi k. Let's write it this way. And then if I sum over k, I see that the sum k equals 1 to 3 phi k squared is equal to exactly the length of d1 psi squared minus d2 psi squared minus 2I inner product, Euclidean inner product of d1 psi with d2 psi. Okay, so what do we conclude from this? We conclude that this sum is equal to 0 precisely when both the real and imaginary parts of this complex number are 0. But another way of saying these two equations is to say that this sum is equal to 0 here if and only if my original coordinates are isothermal. Okay. And now finally, well, we have really a couple of final things to prove. So the first one is the following lemma. And this lemma says that, again, I'm going to have so let's just summarize this. Okay, so what does this lemma say? It says that, again, we're going to start with, we have some immersion, and we cook up our auxiliary functions phi, phi1, phi2, and phi3 is above. This mapping is a regular minimal immersion with isothermal coordinates if and only if the three equations are fulfilled. If and only if, so what do we have? We have that the phi1, phi2, phi3 are holomorphic. The sum k equals 1 to 3 phi k squared equals 0. And finally, the length of phi squared is not equal to 0. So we've already seen one direction of this lemma. So we have shown one direction. Now let phi 1, phi 2, phi 3 be holomorphic functions satisfying that the sum phi 1, phi 2, phi 3 squared equals 0, and the length of this vector squared is non-zero. And then we can define the kth component of the immersion as the real part of the line integral phi k of the complex variable z dz. And this really completes the proof. So what do we see? We see that the existence of a regular minimal immersion in isothermal coordinates is equivalent to the existence of three holomorphic functions satisfying these two equations, that the sum of the phi k's is equal to 0 and that the sum of the squared lengths is non-zero. Okay, so the final thing we need to show is that any minimal surface admits isothermal parameters. Okay, so what is the content of this lemma, really proposition theorem, whatever you want to call it? It says that if I have a minimal surface, I can always locally find a small neighborhood with isothermal coordinates. In fact, this is true in general. Any surface, any immersed surface will emit any smooth surface, any regular surface will admit local isothermal coordinates. There are very sharp theorems about like how big you can take the coordinate system, and I can provide some references for those precise statements. There's a very nice proof of the existence of general isothermal coordinates by Chern, which is, I think, very approachable. But let's prove this in the case where we have a minimal surface. So what do we have? Well, locally, I can write this surface as a graph of some function let's call it f. What does this mean? This means that I have a local parameterization u1, u2 gets sent to the point u1, u2, some function evaluated at u1, u2. Okay, so what does this, and what does the fact that I have a minimal surface mean? It means that just a sec. So remember what we have here. Right, so the minimal surface equation for F is something we can write as F11, 1 plus F2 squared plus F22, 1 plus F1 squared minus 2 . And I can write this equation in divergence form as 0 is equal to the divergence of gradient f divided by square root 1 plus length of gradient f squared. And let's write this as d1 f over square root 1 plus d1 f squared plus d2 f squared plus d2 . Okay, so as a little bit of notation, we might call okay, so we see from these equations that there exist functions. I'm going to call it capital F and capital G, such that D1 capital F is 1 plus P squared over W, and D2F is P times Q over W. And so the existence of these functions comes from what do I have here? Here I have that the derivative, right? So this equation here, I can write as D1 of P over W is equal to minus D2 of Q over W. If I differentiate this with respect to U1 and this with respect to U2, and I use my identity that I have over here, I find that they're equal. So that tells you that I can integrate these two equations to obtain my function capital F. I can also have a function capital G which satisfies D1 G is equal to P times Q over W, and D2 G is 1 plus Q squared over W. And now I'm ready to define my isothermal coordinates, and we're going to set C1 to be U1 plus F of U1, U2. Let's write this properly. C1 is U1 plus F of U1, U2, and C2 is U2 plus G of U1, U2. And then we see these equations imply if I differentiate C1 with respect to U1, I obtain 1 plus P squared over W dC1 du2 is going to be P times Q over W. dC2 du1 is going to be also P times Q over W, and dC2 du2 is 1 plus Q squared over W. So the upshot is that this defines an invertible change of coordinates. Okay. With the Jacobian, given by that. Okay, now I can invert this change, and I see that I forgot a J here. There should. So then when you compute the change of parameters, okay, so what do we see? We see directly from this change of variables that with respect to our new choice of coordinates, the metric is diagonal. We have isothermal coordinates, and that completes the proof. So there's one immediate corollary. And what is the corollary? It says that if how do I say this? If F solves the minimal surface equation, which is the same thing as saying that the graph of F is a regular minimal surface. So if I have a regular minimal graph, then what do I know? I know that I can always locally find isothermal coordinates on this graph. And second, what do I know? I know that if I can find isothermal coordinates, then the restriction of the coordinate functions to that surface must be harmonic. But F was really built out of the restriction of the coordinate functions. F is, in fact, one of the coordinate functions restricted to the surface. So this original function must be real analytic. Okay, so that is going to finish our discussion of isothermal coordinates for today. We'll resume the next time with a proof of Bernstein's theorem.